Hello, physics fam. We are going to do another forces problem. We have a car accelerating at 1.6 meters per second squared, and we're given the coefficient of friction, and they want to know what the force is that the engine is supplying. So we're going to draw a force diagram first. We know that we're going to have normal force because the car is on a surface. And we know that we're going to have weight force because we have mass and we are on Earth. So the Earth is pulling on us, just like we are pulling on the Earth. The car is going to have some type of force provided by the engine. So we're just going to go ahead and call that an applied force. And then we're going to have some friction. So it doesn't specifically say that. It says that we have a coefficient of friction. So that implies that there is some type of friction. Now be careful because this coefficient of friction is not our force of friction. That is our mu value. So just keep that in mind. So if we know what the mass is, over here, the 1.2 times 10 to the third kilograms, and we know that we are accelerating at 1.6 meters per second squared, we know that we can solve for our net force. So we have the summation of forces equals mass times acceleration. So we can say that our net force is 1.2 times 10 to the third times 1.6. So we have a net force of 1,920 newtons. Now that doesn't tell us the force supplied by the engine, but it does help us out. So we know that our net force is going to be a combination of all of our forces horizontally. So we know that net force is actually going to be rewritten as our applied force, or the force supplied by the engine, plus a negative force of friction. And that's going to be equal to our 1,920 newtons. So we're solving for our applied force, so we need to figure out a way to find our friction force. So that's where the coefficient of friction comes in. We know that with kinetic friction, we have the force of friction is equal to mu times our normal force. So we have mu, so that's a check. We need our normal force. So let's go ahead and rewrite this anyway. We have force applied, and we'll go ahead and write minus mu times normal force. And that's going to equal 1,920 newtons. So we need to find our normal force. So we're going to have to look in the y direction. So adding up all of our forces in the y direction equal 0. And that's because we have no motion of our car vertically at all. So we can say from this that our normal force equals our weight force. So normal force ends up equaling the 1.2 times 10 to the third kilograms times 9.8. So we end up with 11,760 newtons. And we can use this in our current statement in the x direction. So again, we have applied force, what we're solving for. We have mu, which is 0.15. And then we have our normal force, which is 11,760 newtons. And that's going to be set equal to 1,920 newtons. Once we've simplified the left side, we end up with force applied minus 1,764 newtons, equaling 1,920. So we'll move that over to the other side. So our force applied, or the force that the engine provides, will be 3,684 newtons. So to review the process, we identified all of our variables from our problem, and then we moved to creating a force diagram where we determined our net force and then set up Newton's second law in terms of x values, realized we didn't have enough information, so we went and set up Newton's second law in the y direction, and then eventually came to our conclusion of our engine force being 3,684 newtons.